All right, good morning, ladies and gentlemen. I'm coming to you from the CSIR. I'm David Mandaha, Media Relations Manager, so I'll be chairing this media briefing today. The media briefing is all about, celebrating young people who are doing well. So the CSIR has actually planned this media briefing to share some of the technologies and the research that young people are working on here at the CSIR. So today we are focusing on 4IR innovations and really looking at what are some of this innovation and the impact thereof on the healthcare system. So our researchers, young researchers, are going to share this work that they are doing in order to improve the South African, healthcare system, but of course using 4IR technologies. So we do have 3 young researchers who will then give us, their presentation. Immediately after presentation, we will then allow for a question and answer session where you will share your questions. Please do share your questions. For those of you who are joining online, please do share your questions on the chat box so that we can get that, read that to our panel members. So, ladies and gentlemen, immediately after that, we have a tour to the learning factory where some demos will be conducted for those who are attending us physically. But online, I think we are going to share pictures. Ladies and gentlemen, without wasting any time, I'm going to invite our first speaker, who is going to talk more about machine learning, and also the powered diagnostics technologies that they are working on as a team. So I will now invite my colleague, who will then be able to share. Before they do their presentation, they will go through their background as young people, where they started, and a bit of motivating young people about their career journey, and then from there they will then go into the demonstration. So I'm going to call Kabe, let's say to be part of the team who will be starting sharing, and then after that he will be joined by Mulani Toy. Immediately after that, we'll have Sipho Chauke, who then share their research work as well as a career journey. Let me not waste any time and invite Gab. Thank you.
Thank you very much for this opportunity to highlight you about the work that we are doing. My name is Abel Telese, and today I'll be talking to you about the machine learning powered diagnostics. To start with, I would like to show you a bit of my journey, where I started and where I am currently. I started my journey with the higher institutions from the University of Limpopo, where I did a BSc in mathematical sciences. I had a major in computer science and physics. And I further went on to do the BSc in physics, BSc honors, at the University of Limpopo again. And then I went on to do the MSc, the Masters of Science in Physics, from the University of Limpopo again. And then I did a second master's in mathematical sciences from the University of Western Cape in collaboration with African Institute for Mathematical Sciences. And then I hold again a certificate in business management from a certificate in business management from the European School of Management and Technology, known as ESMT Berlin. I am currently a PhD candidate in biomedical engineering at the University of Cape Town in collaboration with CSIR. So that's just a short journey of where I started and where I'm currently at. To tell you a bit about machine learning powered diagnostics, we're not talking about a machine learning powered diagnostic device. We're talking about a system that uses advanced machine learning algorithms to automatically diagnose multiple diseases with improved accuracy and speed. So how this machine learning algorithm works is that after you train the machine learning algorithm, you train it to analyze a certain disease or multiple diseases, depending on which one you're focusing on. And then the output or the results of that, they're based on the mathematical or statistical functions. So what runs inside this machine learning algorithm is mathematical and statistical functions. Now, these mathematical and statistical functions, what they do, they help us to automate the diagnosis of the multiple diseases. Now, why are we using this machine learning diagnosis? We have identified some few problems. Now, to start with, maybe let me highlight the key aim of what we are trying to do. This machine learning powered diagnosis, what we are trying to do is to try to help in remote areas where there's limited access to medical facilities. So where there is a lack of diagnostic tools in remote areas, that's where we come in to do the diagnosis. And then again, for example, you may be aware that when you do the test, it takes a bit of time for you to get your results. That's one of the issues that you want to address. We want to give you the immediate results. And then imagine in a case where we're having an infectious disease, and then the results are taking time for it to come. At that time, you might have infected upon many people. And then once you get your results, a lot of people are then again infected. So we want to bring into attention that issue as well. What we want to do here is to give you your immediate results so we can take necessary precautions dealing with a certain disease. For example, let's say now we are having a newly appointed medical practitioners working in a field where they have to do the conventional methods of doing the diagnosis. They are more likely exposed to make errors, human errors, which are acceptable, of course. But what we're trying to do again is to reduce those errors as well. Now, since we are working on technology, we are focusing on the multifunction. Simply meaning we have to as well work in different areas, not specifically focusing on one area. So again, we are applying our technology in the medical institutions, where, for example, we are having a lot of people doing tests, and then we are having a large number of tests to analyze. So we are coming in there as well to automate that diagnosis or that analysis. And then we can as well reduce the delayed output or the delayed results, so we can give the immediate results. Now, what we do, we carry on the artificial intelligence technologies to perform this medical diagnosis. What we do this diagnosis, we do diagnosis based on these samples. Now, our main focus is the patients. Any person who wants to do the test, either at a remote area or at a medical centers. So how we work is this one. We are having our software part, which can work on the internet. Like it can get the results and then it connects to one of the models and then it do the analysis. Imagine having it in the mobile clinic, running on your laptop, for example, something that is accessible, something that is there at that particular time. We can run on our laptop to do the diagnosis based on the internet. Again, we can connect to the medical centers to run their results remotely. So how this works is, it works this way. If you're having the medical centers And then they're connected to all of the database, because now we are talking about fourth industrial revolution. We're talking of automation, and we're talking of medical of Internet things. So if we are having the databases where all of the medical facilities, they store their samples, for example, what we can do, we can connect it as retrieve all of the samples, and then diagnose all of the samples or analyze them, and then send back the results to them. Even when we are having the mobile clinics as well can take the samples and send them to the database. And then that's when we come in to do the analysis and send back the results immediately. And then the medical centers now, they can generate the report and then give the patient their results within a short period of time. So that's what we are doing. But the question now becomes, yes, we are working on the internet. What happens when we're getting into areas where you don't have a network coverage? Now, on that case, we are developing a second component into our project. That second component, it includes the hardware components. So that hardware components, we're going to import our software inside it. So what it's going to do, it's going to convert the samples into digital samples, and then it analyzes them to produce the results without even being connected to the internet. So that's the hardware component of it. And then with this one, it can work like in a remote settings where we don't have the network coverage. Now, the question with working under artificial intelligence is, can we trust it? That's the big question. Now, how are we going to win the public that this is the way to go? Remember, the public, they trust doctors and machines. That's the reality. And when we start with the doctors as well. We're relying on the doctors or on the medical professions. So the medical profession, they perform the tests. They identify what is positive of a certain disease and what is negative of a certain disease. And they identify what the difference between those two samples are. So what we do is we collect their results. And then we're collecting their positive and then their negative results. We put them inside this machine learning algorithms that we are developing. In other ways, we are saying we are teaching the machines the difference between the positive and then the negative samples of a certain disease, but we can work on multiple diseases. So now once our machine learns that this is a positive sample, this is a negative sample, depending on the features that it's detecting on those two samples. And then we train it on those particular results. And then after training it, we'll be checking in the accuracy of it, how accurate it is, how precision is it when identifying those. And then we test with the other samples that it hasn't seen before. Like in this case, when you say the samples that it hasn't seen before, it's like when you're taking a sample from someone and then you test, knowing that this is positive first, because we want to see how it works. So that's what we do. That's one of the tests that we have to make sure that now our algorithms are performing accurately so. Now, just to share with you a bit about these algorithms, we're already testing a software in the lab currently. And then the software, we were testing in about on TB. We had 1,000 patients. And then we wanted to see if it can be able to classify or to detect those who have TB and those who are healthy. So with this, we acquired 99.5% accuracy of classifying those results. And then with all of those 1,000 people, we managed to classify all of their results within a second. Imagine if you were having a sample of 1,000 people and then you're able to give them their results within a second. So that's what we basically do. That's what we're basically testing. We have presented the work last week to showcase what we are doing. And then we just want to go through the intensive testing of it, because what we want to do, we just want to improve it maybe close to 100%. We're giving about 99.5 currently. So we have detected some other. We can train it more to improve it maybe significant figures towards 100%, because now we are working in medical fields. We don't want to get wrong results. So after that, that's when we can now employ it into the real world, where now we can make it work in remote settings or maybe in medical facilities. That's where we are currently. Now, what we want to do, what we want to achieve here is to automate this diagnosis. Like if we are thinking about maybe say 1,000 people testing, if you can automate the diagnosis of their results, and then we give their results within a second, that is one thing we want to achieve, and we are moving towards that direction. The other thing is we want to reduce the time compared to the conventional method that may involve a human involvement when doing the tests. And with that, if you are successful, we are trying by all means to reduce the infection of the disease. If we can diagnose you earlier, and then we find that you are positive of a certain disease, that's when we take the necessary precautions. And then in that case, imagine in the time of COVID-19, for example, where we had COVID-19 infecting thousands of people a day, and then you have to do the test and wait for result maybe tomorrow, for example, or after certain hours. And then after, within a minute, you can infect about many people. So, but if we can give you within a second, you see, we can guarantee you, for example, and then we manage to control that. In that way, we can reduce the death rates, and then we can control any other disease. And one important thing to mention with this is this system, it can work, it can be trained on different things. Should we again encounter a situation where we are having a COVID-19, for example, a pandemic that may come off of another different disease, we can be able to work with it as well, depending on the results that we're getting from medical professions, that we can train our model to work on. Now, this technology is just to be accessible to South Africans and to Africa as large, to help them avoid this disease. That's all from my side. Thank you very much.
Thank you very much, Fabe, for that great presentation. I would like to now call Mlan to come and share his work that he's doing. Over to you, Mlan.
Good day, everyone. My name is Pumlani Choi, and I'll be sharing with you a brief overview of SPR. SPR stands for surface plasmon resonance, and this is a type of an optical biosensor. So just to give you an outline of my presentation, I'll include my education background, introduction, the available types of biosensors, principle of biosensor, the surface plasmon resonance, significance in the 4IR, and the market opportunities for this technology. So again, my name is Pumlani Choi. My first name actually is Michael, and I prefer Pumlani. And I graduated at the University of KwaZulu-Natal in Pietermaritzburg. So I'm originally from KZN with a Bachelor of Science majoring in biochemistry and genetics. I did my postgraduate at the same university, did my honors in genetics, and then master's in biochemistry, and I'm currently at the CSIR through a PhD studentship program. I'm at the National Resistance and Biophotonics. My current project is a detection of SARS-CoV-2 mutations through laser-based biosensors. So to take you back to maybe something that we all already know about SARS, that it had different variants, and these variants were all genetically different from each other, and maybe everyone knew that SARS had a lot of variants, but maybe not know what these variants were. And so the merging of these variants resulted in SARS being a bit more dangerous sometimes, so less susceptible to vaccines because of these variants' genetic makeup. So the genetic makeup of the variant differs from the previous one through something that we call mutations. So mutations are just changes in the genetic makeup of a microorganism, in this case, a virus. So as it changes, so this is a strategy that viruses use to adapt and survive. So they keep on mutating and to adapt it so they gain better adaptability in their environment. So what we're trying to do is to try and detect these mutations. Mutations are very small changes, so sometimes it's just a single base change in the genetic makeup of an organism. So they're very small changes, and they're quite hard to detect. Well, real time or with the naked eye, it's pretty much impossible. So what we learned is these variants of concern that kept on emerging through SARS were hampering the development of vaccines because we could not treat these variants of concern because they are all different from each other. And then so it's again all through these viral mutations, and these mutations were all unique from the different variants. And then so the mutations occur in a phenomenon called antigenic drift or shift sometimes. So I'll get to this just now. So a shift, antigenic shift, is when a virus is mutates in a major, resulting in major changes in their genome. So a shift usually results in a pandemic. So this is the similar case with SARS-CoV-2. A drift is the accumulation of mutations over time, and so this could be, mutations could be both beneficial or harmful. Humans sometimes do also happen to mutate on their genomic makeup to result in more adaptive, better adaptable species, and this is good mutations. But viruses usually, it's bad mutations for humans, but maybe for them it's good mutations because they can adapt better. And then so what we realize with these mutations is because they're so quick sometimes, especially with the SARS-CoV-2, we need a fast and a reliable prediction tool for these mutations. And then so usually in a molecular technique or molecular lab, to detect mutations that you already know of or you suspect, use methods like PCR, DNA microarray, DNA sequencing, or multiplex location-dependent probe amplification. But if you had mutations, say if you had, say, SARS-CoV-2 mutating into a variant that you're not sure of its genetic makeup, how it looks and how it behaves, you use a method called sequencing. And then this is, as you can see, it's quite a long process. It needs a lot of reagents. And also this introduces a lot of bias and human errors on it. So what we are proposing is the use of biosensors. So biosensors are basically biological sensitive layers that convert biological changes into a detectable signal. So these biological changes, again, could be different mutations for different variants. So there are different types of biosensors, electrochemical, thermometric, bioisoelectric, magnetic, and optical biosensors. And this is what we are focusing on, the optical biosensors. So what are optical biosensors? So optical biosensors are pretty much nanophotonics. So they analyze optical signals for output. So nanophotonics explains this a bit better, maybe for people who are not familiar with, well, non-science people. So nano means small, bio is like biological material, and photonics, maybe this is science. Photonics is just a quanta of light, so it's a photon. So it's it's a size light. And then so what biophotonics uses is three components: biological elements, optical element, and a signal output. So biological elements could include nucleic acids. These are DNA, RNA, or proteins, antibody cells, to convert through optical element. These are SPR, LSPR, gratings, photonic crystal, resonators to give you a signal output that can be detected through a photodiode, CCD camera, or sometimes a smartphone. So what we are focusing on is optical biosensor made surface plasmon resonance, or FPR. So what this technology does is, so it uses light to excite oscillating electrons. So I know that sounds a bit too much, but what happens is you have light pumped from a light source. It hits the surface, the metal surface. Most of the time, the metal surface is usually coated with gold or silver sometimes. So as light hits this surface, it excites electrons from the actual surface. So these electrons oscillate. So oscillating means they go up and down, and it creates this concentrated wave energy. So this is what basically this means. So metal dielectric interface. So this is when the metal surface, say your gold-coated surface, get heated through a light, it results into this dielectric interface. So electrons moving up and down. So this results into a very sensitive surface, metal surface. So it's sensitive to changes. So anything you put on top of this surface gives off a different signal. And then you put something else, gives you a different signal. And then so now, because mutations are very small changes, you need something that's really this sensitive into changes. So if you have to put, say, SARS-CoV-2 alpha variant, it should give you a certain signal, and you have to put SARS-CoV-2 gamma variant, it should give you a different signal. And but we know these variants of content, there are very slight differences between them. And then so this surface again has energy that is confined into a small area. So this energy that's confined in a small area, this is what we use to detect. So this energy is called a density wave. So it's density wave because every time you change the density on this surface, you get a signal, this optical signal that you detect through CCD cameras or smartphone. And so the significance of this, so what we're trying to do at the moment, this is a lab-based technology, but what we're taking from this is the actual performance and the actual characteristic of light on the surface. And then this gives us a direction into developing a point of care device. So we can use light, we can use white light, we can use lasers to excite electrons on the surface, and you can test thousands of people in isolated areas, limited resource areas. I mean, you can use your smartphone to detect these changes. So this is where we're going. We believe this will be a very reliable tool. Also, with growing interest in laser-based techniques, now we're trying to develop a point of care diagnostics to detect these mutations, because we know viruses are everywhere, and we might still have a pandemic emerging out of nowhere and still mutate. And so this is maybe puts us in a better position than we were before, maybe a bit more prepared for future pandemics now. So this is where we go with this technology. And right now it's not available in the markets, but maybe by conservative estimates, maybe we say 3 years, because my project will run for 3 years. And then after that, we'll see if we have it done. So that's all from me. Thank you so much.
Thank you so much, Lan, for that presentation. So our last presentation will come from Sipho Chauke. So I'll hand over to you, Sipho, and then after that, if there are questions, we'll pose the questions to the young scientists. And then immediately after the session, we'll go to the learning factory. That's where we're going to see the demo. And I also suggest that the one-on-one interviews maybe may happen there at the learning factory. Over to you, Sipho. Thank you.
Thank you, David. So as David said, my name is Sipho Chauke, and today I'll be telling you guys about my project, which is on an optical-based biosensor for Mycobacterium tuberculosis. So Mycobacterium tuberculosis is just the causal agent for TB. Okay, so a little bit on my qualifications and my background. I have a master's degree and an honors in medicinal plant science from the University of Pretoria. Then I have a BSc in biochemistry also from the University of Pretoria. I am also professionally affiliated with the South African Society for Microbiology. And I'm currently working on research that is focused on TB diagnosis and detecting TB using optical-based biosensor. So before I start, I would like to share a quote with you guys about basically today's whole theme. And this quote is by Franklin D. Roosevelt. So it says, "We cannot build a future for our youth, but we can build our youth for the future." So I think this quote ties in perfectly with encouraging young people to pursue careers in 4IR, because let's face it, 4IR technologies are our future. So a little bit of background on TB is that TB is a respiratory disease, just like COVID, and it is one of the most infectious diseases globally. So it kills approximately 1.5 million people per year globally. And imagine if you could detect this disease before you spread it to other uninfected individuals, and you initiate and start treatment before it becomes worse. So there are conventional TB diagnostic tools that are available. However, they may be costly, and the time to get your diagnosis often takes several weeks. So this brings me to the problem statement. But before I share the problem statement with you, I just want to mention that TB on its own, TB testing and TB diagnosis on its own is a daunting task. Now imagine TB testing or TB diagnosis in a resource-limited area such as the rural areas. So this is the problem statement, that we want to find ways in which we can diagnose TB in a sustainable way, at a rapid rate, and the diagnosis can be done at a large scale. So you might be wondering, what is this technology? Before I share with you what this technology is, I'd like to share with you a few aims of what this technology was trying to achieve. One of those aims was to approach TB diagnosis in a sustainable way, so that it is accessible and affordable to ordinary South Africans, and that TB diagnosis can be done in remote areas and at a point of care setting. Because let us face it, if we can diagnose TB, then we can reduce the number of TB infections or the number of TB deaths that we see yearly. So this technology is called an optical-based biosensor. And you might be wondering, how does it tie in with the 4IR innovation or the 4IR technologies? So it falls under the advanced engineering nanotechnologies, but it is a medical technology that is focused on diagnosing infectious diseases, and more specifically TB. And this is so that we can diagnose TB at a rapid rate and at a larger scale, and obviously at affordable prices for ordinary South Africans, keeping in mind remote areas. So how this technology works is that it uses light to diagnose TB. So it captures the TB DNA within samples and gives you a diagnosis. So the technology that goes into making this optical biosensor allows it for it to be a miniaturized biosensor. It therefore gives it the advantage to be used in remote areas. It can also be used at a point of care, and it is at no hassle, especially if there is no electricity. So that is also one of the added advantages of having an optical-based biosensor. So you might be wondering, when will this technology be ready? So right now it is not in the market, but as it is an ongoing project, it can be expected between 2 to 5 years. And this technology will definitely help healthcare systems that are focusing on TB diagnosis. And thank you for your time.
Thank you so much, Sipho, for that great presentation. I think we have come to the question and answer session. If we have any questions, I'll start to check with the online colleagues if there is any. None, I think we'll pass that. The group in here, do we have any question? We don't have any questions. I think what we are going to do now is that we'll close this session and then we move to the learning factory where you will then see some of these technologies, you know, the 4IR technologies. And I think that's where you can have, you know, one-on-one interviews then with our young researchers. I would like to thank you all for coming. And thank you all those who join us online for being with us today. We will be circulating the media statement as well regarding this and some pictures thereof. Thank you.
I understand what you